Hello friends, this video on Thermodynamics part 18 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched part 1 to part 17. First, enthalpy, we discussed internal change. Have you ever thought how many types of enthalpy are there? There are various types of enthalpy. The first is the enthalpy change for reaction, where the reaction takes place. In reaction, we can have a formation reaction where, for example, you have H2 plus O2, you make H2O. So you'll call this enthalpy of formation, or you have combustion reaction, you burn this carbon, you get CO2, or you can have neutralization reaction. You have, let's suppose, HCl plus NOH, acid plus base, you get NaCl plus H2O. There is an enthalpy change here. You can have enthalpy of solution. You have some solid, you mix in liquid, it becomes solution. You can have enthalpy of hydration. I think CuSO4, for example. You add with water, it becomes CuSO4.5S2. This kind of reactions. So these are all the reactions. These are all type of enthalpy of reaction. And there are subcategories: formation, combustion, neutralization, solution, or hydration. The next big category of enthalpy change is the enthalpy facing transformation. Even if the substance transforms the stage, it may go from here, if you see liquid to gas, here it is gas to solid, here it is solid to liquid. So all this stage change, solid to liquid, liquid to gas, gas to solid. So all this kind of stage change also has change in enthalpy. And we'll talk about those things in the enthalpy of phase transformation. We also have something called bond enthalpy that deals with the change in enthalpy between bond formation, bond breakage, lattice formation. Those kind of things will deal in the bond enthalpy. So let's start with enthalpy of reaction. So the enthalpy change in the reaction is called reaction enthalpy. So if you have a reaction, that if there is an enthalpy change, you call it enthalpy of reaction. I think we have introduced this term. It's denoted by delta H with the R symbol. R stands for reaction. You see, the symbol is delta H. And if you want to find the delta H of R, delta H R is enthalpy of reaction, you find the sum of enthalpy of product and subtract with the sum of enthalpy of reactants. What you get is the enthalpy change for a reaction. Right? You find the enthalpy of product, you find the enthalpy of reactant, just subtract them, you get the enthalpy of the reaction. A typical example can be, this is my reaction. We have methane, you burn the methane, you get carbon dioxide and water. So if you find the enthalpy of this reaction, that will be nothing but enthalpy of the product minus enthalpy of the reactant. If you do that, you get enthalpy of reaction. We'll take some examples to show that how to get. So enthalpy of this methane, oxygen, carbon dioxide, water, these are all standard values which are found by the chemist, and they have given a table to us so that we don't need to reinvent them. We can just use the values they have found using experiments, and then we can find enthalpy of the reactions if we know the enthalpies of these methane, oxygen, carbon dioxide, and water. So we have enthalpy, but is there any standard enthalpy? So when you talk about standard, for example, I talk about standard at temperature and pressure. That means we fix a value of temperature and pressure so that it is easy for scientists to communicate also, right? So we also have the standard enthalpy of reactions where we have standardized things, right? So if you see this enthalpy, it depends on the condition where the reaction is carried out. So it is necessary that we standardize things. So the standard enthalpy of reaction is nothing but enthalpy change in their standard state. So when they say that the substance are in their standard state, that means they are in the pure form, they are at 1 bar pressure and 298 Kelvin temperature. Please note it is not 273, it is 298 Kelvin, that is almost 25 degrees Celsius. That is the temperature. And the chemists have taken that this is the standard temperature for most of the thermodynamics thing, because you can't have thermodynamics reaction at 0 degrees Celsius. So they have taken 25 degrees Celsius, that is 298 Kelvin as the standard temperature, 1 bar atmospheric, 1 bar pressure, the standard pressure, and they expect the substance to be in the pure form. That is the standard thing here. So if you have a pure form of substance, 1 bar pressure and the 1 temperature, 298 degrees Celsius, 298 Kelvin temperature, what you get is the standard enthalpy of the reaction. So now how to tell whether this is standard enthalpy or not? This is done by adding a superscript V, the symbol, this V, that says that it is standard enthalpy. And finding it is almost the same formula. Standard enthalpy of reaction will be, you say the standard enthalpy of product and you find the sum of standard enthalpy of the reactant, right? Standard enthalpy of the reactant. You subtract it, that gives the standard enthalpy of reaction. As I told, in the enthalpy of reactions, we have different kinds. The first was the enthalpy of formation. So, if the enthalpy change accompanies formation of a compound from some reactants, that type of reaction, that type of enthalpy is called the enthalpy of formation, where you are forming something, right? For example, you add carbon and dioxide, you form CO2. So, if you are forming carbon dioxide, such example is enthalpy of formation. Here, in this case, delta H is minus 394 kilojoule. Correct. So, if you form some product, then you can say as enthalpy of formation. The symbol is, I think, delta HF. Enthalpy of formation. Here also, since we have enthalpy of formation, we have standard enthalpy of formation also. Same thing when all the species in the chemical reaction are in the standard state, that is, things are pure, 1 bar pressure, 298 Kelvin temperature. So it is called standard molar enthalpy of formation. Here also same thing, same formula, because anyway it's all the same parent. Standard enthalpy of formation, you can say nothing but standard enthalpy of product minus standard enthalpy of reactants. As I have told so many times, if you want to find standard enthalpy of a reaction, you have to do a summation of standard enthalpy of reactant and product and subtract with the product. So if you see here how to find that, for that the chemists around the world, they have given us a table. So for example, if you want Al2O3, standard enthalpy is given. If you want CaCO3, standard enthalpy is given. For sodium chloride is given. For carbon it is given. So for all these they have given the standard enthalpy of formation. So if you want to find standard enthalpy of reaction, you can, for example, if the reaction involves C plus O2 is equal to CO2, so you'll find enthalpy of CO2 somewhere it is there. This guy will take 394. I'll just take a pause. Minus carbon and oxygen. Carbon is 0. Oxygen is how much? It's not in this table, maybe in the other table. So if we add the enthalpy of oxygen from some other table, then we'll get the whole enthalpy for this reaction. We'll take some examples on that. So we'll take one example. We'll have to calculate the standard enthalpy of formation of C2H4 from this reaction. So we need the standard enthalpy of formation for all these values, H2O, CO2 and O2. We have to create a table, or let's assume that the question has given these values, delta HB for this. So we have to find what standard enthalpy of formation of C2H4. And enthalpy of a reaction is given. So if you see delta H standard for this reaction R is nothing but sum of delta H for product minus sum of delta H for reactant. Correct? So for product I have carbon dioxide and water. So for carbon dioxide the value is 3 minus 393.5 and there are 2 moles of CO2. So 2 into minus 393.5. Why I multiplied with 2? Because all these values are extensive properties. Plus product we have water also, 2 molecules of water, 2 into, for water it is 249 minus 249 and everything is in kilojoule per mole. This is the reaction product minus, sorry, it will be kilojoule only. Why? Because we multiplied the mole part to kilojoule, minus 10 enthalpy of reactant. Reactant I have C2H4, so let that value will be delta H, which I have to find, plus oxygen. For oxygen it is 3 molecules and oxygen is 0. We have seen in the last table actually this oxygen is 0. So this is what we get, right? So if you solve this, and this value is something we know, that is minus 1323 kilojoule. So if you solve this now, you get minus 1323 kilojoule. 1323 kilojoule. This total sum, if you do, is equal to minus of 1285 kilojoule minus delta H, which you have to find. So if you want to find delta H of C2H4, that becomes 1323 minus 1285 kilojoule. And that's, if you solve, then it becomes 38 kilojoule. And that is my answer. And that will be in per mole, right? Because this delta H before all these are per mole, so we'll put in per mole. So that is easy to find, right? Not that difficult. So we have to find the delta H enthalpy for the reaction. There is nothing but the delta H of product minus delta H for reactant. This value was given, this value we can find, reactant, this is the value, and we solve this, we get the answer. As I told, the enthalpy change of combustion is also part of reaction, subcategory of reaction. So we have enthalpy change of combustion. So when do we study enthalpy change of combustion? When complete combustion takes place for 1 mole of substance in excess of oxygen. Then we talk about the enthalpy change of combustion. Example, carbon, you burn with excess oxygen, gives CO2. Delta H is minus 394 kilojoule for 1 mole of carbon. Methane, you heat, you burn in excess of oxygen, you get delta H is minus 891 kilojoule. Because this much energy is released, right? And please note that delta H for delta HC, there is the enthalpy of combustion is always negative, because combustion is always exothermic process, and we generally we see that the heat is generated when the combustion takes place. We'll take one example for the standard enthalpy of combustion. A cylinder of cooking gas, which we use in hose, is assumed to contain 11.2 kg of butane. The thermochemical reaction for the butane is this. What we have to do, we have to find how a cylinder lasts. Given that the family needs this much kilojoule of energy per day, and assuming 30% of the gas is wasted for the cylinder. In both cases, we have to find how the cylinder will last. So we have 11.2 kg of butane. So with this thermochemical equation, we can find the energy released by 1 mole of butane. See, 1 mole of butane, if you see, is what? C4H10, right? So 4 into 12 plus 10 into 1, that is 58. So 1 mole is 58 gram. That means 1 mole or 58 gram of butane will give 2658 kilojoule of energy. Correct? That is 1 mole. So we have 11.2 kg. 11.2 kg of butane gives how much? 2568 into 11.2 by 58. This was in gram, so I'll multiply by this much kg. Correct. Daily requirement is how much? 15,000. So number of days it will last is this thing 2568 into 1112 1000 by 58 into 15,000. This is the number of days it will last, because n number of days into this many kilojoule will be the total kilojoule, right? So this will give 34 days. That's the first part, right? How much cylinder will last? But they're saying that the efficiency is 30%. 30% of the gas gets wasted. In that case, how much the cylinder will last? So with 30% gas wastage, that is 70% efficiency, right? 30% wasted is 70% used. It will last for this 34 days into 70%. That is 24. And that is my answer. Correct, because see, 30% get wasted, 70% is used. So it lasts 70% of the days, that is 70% of 34, that is 24 days. As I told, neutralization is also part of chemical reaction, so we'll study enthalpy of change for neutral. So by definition, it is nothing but the enthalpy change in the complete neutralization of 1 gram of acid by a base or vice versa. Example, if you see HCl plus NaOH keep NaCl plus H2O and delta H is minus 57 kilojoule. There is something special to note here, that enthalpy of neutralization for all strong base and strong acid is always minus 57 kilojoule. That's a interesting point to know. Experimentally, they have found that the enthalpy change for neutralization for all strong acid and bases minus 57 kilojoule. With this, we'll take an example on enthalpy change for neutralization. What would be heat release when 0.5 mole of HCl is neutralized with 0.5 mole of NaOH in aqueous solution? Let's have this reaction. HCl plus NaOH gives NaCl plus H2O. So we have 0.5 mole here, 0.5 mole here, we get 0.5, 0.5, 0.5. So for 1 mole, for the same reaction, for 1 mole, we get 57 kilojoule of energy. Since it is 0.5 mole, we will get half of this, that is 28.5 kilojoule of energy. Very easy. See, for 1 mole, the heat release is 57 kilojoule. For half, it will be 57 by 2, that is 28.5. Enthalpy change of solution is also a chemical reaction, as I explained. So by definition, it says that enthalpy change accompanying the dissolution of 1 mole of substance in large excess solvent. So with further addition of solvent does not involve any more enthalpy change. Example, we have KCl, we put in water, lot of water, it becomes KCl aqueous, and after that, even if you add more water, there is no enthalpy change. And for this, the delta H is plus 18.6. That means it needs this much energy. Copper sulfate, if you put a lot of water, it becomes copper sulfate aqueous and releases 66.6 kilojoule for 1 mole of copper sulfate. So these are some of the examples for the enthalpy solution, where you have a substance which you dissolve in excess of solvent, and you keep dissolving it till the point where you see that there is no more enthalpy change. As I told, hydration is also a type of chemical reaction. So for that also we have enthalpy change. The definition says that enthalpy change for hydration is nothing but you have one hydrous salt, hydration of 1 mole of an hydrous salt by combining the specific number of water molecules. So it is 1 mole actually, not more. So we have 1 mole of anhydrous salt and you combine with water. Example here, if you see copper sulfate, you have this 5 water molecule, you make its copper CuSF4.5H2O, you get this much enthalpy change, you get this much change. So hydration and solution, if you see, in both cases we add aqueous solution, generally water, but in case of enthalpy change for solution, we add lot of water, excessive water. But in case of hydration, we add only specific number of water molecules. For example, if copper sulfate, we add 5 number of water molecules to get CuSF4.5H2O. But in case of the enthalpy change for solution for the same copper sulfate solution, we add plenty of water. We keep adding water, and then we get this enthalpy of solution. So both are different. I think you must be knowing that solution reaction and the hydration reaction. Hydration reaction, we add specific number of water molecules. In solution reaction, we add plenty of water or aqueous solution so that the whole thing becomes aqueous. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.